Hi everyone, my name is Asma Kassab and I'm the R&D Engineering Supervisor at MOGAS Industry. I hope everyone is safe in this pandemic. Today's presentation will be virtual, so if you have any questions, you can reach me in this contact information here, and I also have it at the final slide. In today's presentation, I will be talking about purging philosophy in delay cooker valves. MOGAS is a severe service company, so in most of our applications we need some sort of purging to clear the body cavity. So purging in general, just a quick introduction. In severe service application, when you operate the valve on and off, there will be some residuals from the process fluids that we need to clean to maintain operation and improve performance. MOGAS is dominating the severe service market in heavy oil applications. In this particular presentation, I will be discussing the delay cooker side. In fact, any lack of insufficient in the valve may cause interruption to the process and valve may lock up. The right-hand side is the R&D valve where we fill the body cavity with some sort of material to simulate the coke buildup. We've done this testing in the R&D where we were looking to see the effect of purge with or without purging. We still have this valve in the R&D, and I will be happy to show it to you if you'd like to tour the facility. Also, we've given a detailed presentation about the testing in RefComm last year. In this presentation, again, I will be mainly going through the delay cooker discussion. I had several presentations discussing the heavy oil side in valve world. I will be happy to discuss it offline. The main objective. So this is our installation for the switch valve DV4, and as you can see here, there is a lot of purging involved. Before we started this delay cooker concept, we had a very aggressive target from marketing and sales regarding steam consumption and how to minimize it. So for this concept wasn't just performance, also the convenience of the customer reducing the consumption of steam. So we paid a very close attention to the purging in these applications. I personally used CFD, which is Computational Fluid Dynamics, and testing validations to purge the delay cooker purging concepts. We have 3 patents, 2 for the DV4 and 1 for overhead and isolation valves. The one for I will be discussing all of them next. The first one we will start with is the MOGAS 4-way switch valve. This is the 3D model, and this is the actual to scale a 12-inch 600 valve. These two are 2 of the purging that we have. This is the flow will go in, and this is drum A, and you have a drum B. So we're purging behind the 2 drums. There is another purging on the top in here that's in a very specific angle, which I will discuss next, and lateral purging. We also have 2 drains. So this is the bypass. If you see it, it's in the other end. We have 2 recommended drains for this DV4. So just as a quick introduction on how we do the CFD model, we start from SolidWorks modeling. This is just a cut view of the DV4. The exact location of the purging and the drains, it took so many trials to exactly come up with the right locations to be able to cover and fully cover the body cavity. As I mentioned before, we have 2 in the back and 1 here on the top, and 2 drains for this design. So for the CFD, you start from the SolidWorks model, and then we extract the fluid volume, which is only this yellowish orange color here. And then this is the CFD model that I will be working with. Testing. So As you all know, for a CFD, it's very critical to validate any simulations. I don't know if you're familiar with this term, but if it's garbage in, garbage out. So you have to kind of know what you're looking for. Definitely testing is very critical to validate any simulation. We've done typically start with CFD because we have endless combination of locations that we can use. And then once we validate a specific or see a potential of a specific location, then we do the prototype and start testing. The testing I did here is something I'm familiar with from my master's degrees. I used fluorescent microsphere particles. These are quite expensive, a few $100s per gram. So it was interesting to try it in such a big scale. I used different colors. So I injected tracing particles from the top, from the bottom, and the third purge, 3 different colors. I used orange, green, and purple. I use something called a collision nebulizer, which is this one. It's like a mist. It will inject some sort of mist, and I generated some sort of like 30 psi, 15-30 psi pressure drop. So simulated what we did for the CFD. The main intention of this was very simple. These are particles that you can see under the UV light. So my intention was, if I take this one, this is a top entry. So if I take this top off and I see tracing particles glowing everywhere under UV light, then I cover the entire area, same as the CFD. So this is what we did. These are pictures of the testing. We built a huge tent because it needs to be dark. This is using UV light. I was lucky that we had one in our cleaning room, an expensive one. So I managed to capture very good pictures. If you see here, this is the one from the top. This is the orange side purge. There is another green one here. And this is kind of showing both ends, the green and the orange. And after disassembling the valve, we can clearly see that the particles covered everything. If you can see here, these two are the seats. If you see the marks, these are the seats. This is when everyone touched the surface. It was very clear that the flow covered the entire body cavity. It was a huge success. So looking into how the CFD looks like. So again, we tried different locations for the purging, and this is what the simulation led us to. The right-hand side is the CFD, and the left-hand side is the testing. This is the green side, which is the one up from the top. It was completely covered with particles once we took the valve apart. The main reason I choose these two because, as you can see here, I managed to cover the back, which is between drum A and drum B. Also, if you notice that I have 2 drains, not just one. When I started with one, all the particles and all the flow go to the flow resistance side, which is this one, less resistance, and there was barely anything here. So I added the 2 to be able to cover the entire area. I don't know if you noticed, but I wasn't very happy about this top here, and that's why I introduced the third purging. As if you can see here, it's not straight. If you have a close attention, it's angled specifically to be able to target the area and fully cover the body cavity with purging. And this one is both combination of purging, this inlet and the second inlet, which I'm calling A and B. As you can see here, it's fully covered. Testing was the same. Everything's covered. We pretty much managed to match the CFD simulations with our testing. I would like to give some time to discuss the steam consumption. So MOGAS design is billable spring. Before they used to use the billow springs, we definitely have a significantly lower steam consumption in the MOGAS design. As you can see here, it's more than 90% less. This was shocking when I first introduced it to our sales. There was a lot of debates why. So from my perspective, it's very simple. It's all comes to the time. In here, we have to continuously purge to clean this seat and make sure it's not gonna lock in the field. Versus in our design, we have an intermittent purging. So we don't have to, we have to continuously have pressure cavity, but not necessarily continuous flow. So this is mainly because we here account for, as I will discuss at the end, 20 minutes purging versus 24/7 running to be able to maintain this one clean. Again, they require a much less flow rate for this purging here comparing to a body purge, but the problem is that it's continuous. This is this is the installation that I was lucky enough to witness, which is the picture I showed in the beginning. As you can see here, we replaced an existing valve, which was a DV4 switch valve. And I noticed that they had to blind flange at least 4 of the purge connections when we installed MOGAS valves, which also speak to this, that we have much less purge ports, so we still have a much less steam consumption. It was pretty cold, as you can see, but it was a very nice experience for me to be in the field and witness my design in life. So this is the second one. We have 2 patents for the DV4, and there is the patent for this MOGAS isolation overhead vapor. This is we called vortex flush. Again, similar technique as we did for the DV4, mainly to flush the body cavity when we need it, and it's simply located in an areas where we thought is needed for this application. So for overhead vapor, typically we're not expecting solids, should be vapor, but you know, things can happen. So we mainly target the bottom because from I know from I did my PhD on particle deposition, so I know that particles simply is gonna settle on the bottom. Whether you like it or not, this is where the areas where everything is gonna, all the action is gonna happen. So we said, okay, then if this is what we know, if it's gonna happen, then we should target the bottom and make sure it's clear. Also from our experience, we know that top of the stem is an area where clogs can happen and it can coke and build up. So we made this tangent to the top, again targeting the specific areas where we know that from surface that's a high potential for coke buildup. This design was very interesting. It was done for overhead vapor and isolation valves. We had a brainstorming session. My office with all the R&D team. We're like, okay, what we should do we do it the same way as we've always done it, which is somewhere here in the middle, or should we think of something else? Okay, we know that everything's gonna settle on the bottom, so can we put it at the bottom here? So my problem was, if you put it in the bottom, everything is gonna go down the drain once the drain is open, so it's gonna be in and out, which is the least resistance. Flow's not just gonna travel all the way. So the idea was, okay, how can we make it not go straight? So should we tilt it? So we came up with the vortex flush idea, which is to use the curvature of the bowl to be able to create some sort of cyclonic effect, motion to flush anything in the bottom. We had a very genius designer. He said, I can make it flush like a toilet. He did. Was his first iteration. We tried several iterations after, and we managed to master the angle that we need to be in. We got the patent, I think this month or last month, final. This is the validation. So again, the concept of just using CFD doesn't work. You have to validate it and make sure it's actually what's happening. The one to the right is if we put it the same way as we typically do in this industry, the purge location. This one is the location where we change the purging to the vortex flush at the bottom, tangential to the bowl curvature. And as you can see here, this was a water testing. So we injected water in to see how the flow is gonna behave. We did use an acrylic pipe, transparent, so you can see it. This is also very familiar technique in college that we used for visualization. And this one, when we remove the pipe. As you can see here, you can definitely see the cone happening. You can see the vortex in here versus the one to the right was more very like random turbulence effect kind of pulses. I have a video next that I would like to show you. Let's see if it will cooperate. Okay, so I don't know if you hear the sound or not. There is an audio, but the one on the left clearly showing a vortex effect versus this one was more random effect. This is matched very well with the CFD findings. Next, so with all the in the CFD we did and we learned, we came up with the MOGAS delay cooker purging philosophy. So the purge locations and operating recommendations. For four-way switch valve, which we call it DV4, we recommend 3 body purges. We call it type 2. Purge at MOGAS, we call the seat as type 1. We're asking for a 0.38-inch restricted orifice for the 3 body purges, and this is the typical purge steam consumption recommended for this specific application. It's the same for the furnace feed isolation valves, which I believe is usually put before and after the DV4. In here, we MOGAS recommend 2 body purges, the same as we did. We mentioned the vortex flush one and one on the top of the stem. And we have 1 seat purging, which is a C1AS MOGAS design. The restricted orifice for the seat is definitely smaller, requiring to purge a much smaller area. For the overhead vapor in the isolation, for this application require a much less steam consumption because simply the pressures for this application is much less. We recommend the same quantities of purging as the isolation furnace feed. The main outcome of the study is that we absolutely need to use a restricted orifice in purge lines to control the flow while maintaining the purge pressure high. Typically, we recommend around 30 to 50 psi higher pressure drops in this application. Probably less for heavy oil applications. I would say 30 is the max for that application, but here we use steam, so we can go up to 50. The steam needs to be superheated, so this is the temperature that's minimum to maintain it as a superheated steam, a dry steam. The main also outcome of this study was that we would recommend using drains. As you can see from all the CFD and the testing we've done, drain will allow you to do flushing. So you can use it for a few minutes to remove anything that was built up inside your body cavity. it will significantly reduce your steam consumption because you're only turning the drain only for a few minutes when you need to flush the body cavity. We would recommend coupling the steam purge with a flush drain operation to clean any coke debris and enable intermittent purging at fully open and closed position. The flushing operation recommendations is very simple. Before you turn the valve on and off, simply cycling it, we would recommend 5 minutes of flushing. And then once we finish the operation, we would like to continue flushing for 15 minutes. After we're done, about 20 minutes total, we would like to close the drain. So this was one of the main recommendations. We can provide it without drains. We've been providing it for customers per request, but the additional of the flushing technique will definitely increase the valve performance and reduce the steam consumption. Again, this is my contact information. This is my email. You can call the office and ask for me. My name is Asma Kassab. We still have this R&D valve in the R&D area. I will be happy to tour it, the facility. Also have one that can cycle and operate. So we have at least 2 for demos right now in the R&D. If you have any other questions about MOGAS, about the purging and other applications for heavy oils, I will also be happy to answer them. Thank you.